Modern edge computing devices are no longer simple CPUs. They've mutated into complex, heterogeneous systems packed with accelerators designed for tensor mathematics. This hardware boom triggered a software crisis. To interact with these new chips, developers must navigate a deeply fragmented landscape of proprietary vendor tools. Silicon vendors are flooding consumer devices with dedicated AI hardware, from Intel Core Ultra processors to Qualcomm Snapdragon and Apple's M-series silicon. The industry's dominant response to this fragmentation is to abstract the hardware using monolithic whole graph compilers, like Intel's OpenVINO or NVIDIA's TensorRT. This creates an opaque, black box execution pipeline. Researchers lose granular control over intermediate layers and are entirely locked out of managing numerical precision. This black box reality directly conflicts with the strict requirements of systems like zero-knowledge proofs or financial compliance, which mandate perfectly reproducible arithmetic. Delegating an entire neural network to a proprietary vendor compiler directly breaks the mathematical determinism and reproducible arithmetic required for auditable machine learning. Loom version 0.81 operates on a divergent architecture. It is a deterministic neural virtual machine, engineered to solve hardware fragmentation through first principles. Instead of relying on a standard sequential computational graph, Loom treats a neural network as a three-dimensional spatial grid. Every operation is indexed by depth, row, column, and layer. At every node, a dispatch layer acts as a split-second traffic controller, inspecting available hardware and explicitly routing workloads down the most efficient pathway in real time. Real-time spatial routing enables explicit surgical hardware targeting on a per-layer basis. It completely bypasses the rigid subgraph partitioning forced upon developers by traditional compilers. Before attempting to control proprietary neural processing units, an execution engine requires a universally portable, high-throughput baseline. Loom establishes this bedrock using a lightweight Go-based CPU core paired directly with a powerful WebGPU execution path. WebGPU generates WebGPU shading language, or WGSL, dynamically at runtime. This avoids ahead-of-time compilation lock-in entirely. This approach is hardware agnostic, running natively on massive desktop GPU architectures like NVIDIA's discrete hardware. That exact same WebGPU codebase scales down to execute on completely different proprietary laptop architectures, such as Apple Silicon, without rewriting a single kernel. While WebGPU covers parallel processing for massive decoder stocks, it is still a monolithic offload strategy. The entire network state must be pushed to VRAM to function efficiently. Securing a unified, vendor-agnostic WebGPU baseline ensures the core engine remains free of bloated software development kits. Only with this stable foundation can the system bridge the gap to highly specialized, fixed-function NPU silicon. The newest generation of edge silicon introduces a complication: dedicated deep learning accelerators, like the NPU embedded in the Intel Core Ultra Meteor Lake processors. These NPUs cannot execute raw shaders. They require proprietary user mode drivers and strict ahead-of-time compilation to translate mathematical operations into specific hardware schedules. To utilize this hardware without permanently linking gigabytes of Intel OpenVINO dependencies into the Core Go runtime, version 0.81 introduces the poly.xl framework. This schematic visualizes the framework's core mechanism, a C application binary interface, or C-ABI. It establishes a strict, standardized memory boundary that completely isolates the virtual machine from opaque hardware drivers. The execution lifecycle requires 3 steps. First, the discover-excel routine dynamically locates and loads the vendor's shared library only if the physical hardware is detected on the host machine. Second, the sync-to-Excel phase passes the master weights for a specific individual layer across the boundary, where the vendor software compiles and bakes them into a hard-coded execution graph. Finally, during live inference, the dispatch layer jump table halts standard math execution. It fires the input tensor across the C-ABI boundary for hardware processing and instantly retrieves the result. A rigid design constraint governs this bridge. Backpropagation and gradient calculations are strictly isolated to the CPU and GPU. They are never routed to the NPU. This dynamic, intercept-driven plug-in architecture allows developers to harvest the raw mathematical speed of external silicon while retaining absolute control over network topology and memory management. If the NPU is designed specifically for artificial intelligence math, and we have a functioning C-ABI bridge, why shouldn't we offload the entire network to the accelerator? The Loom 9-layer performance matrix provides the empirical proof exposing the limitations of whole graph NPU compilation. But when we map the large tier data matrix for dense two-dimensional convolutions, the NPU finally delivers on its promise. On large tier convolutions, the compiled Intel NPU pipeline executes up to 28 times faster than the native software baseline. The data shows that treating an NPU as a universal hardware accelerator creates massive latency penalties. Maximum efficiency depends on layer-by-layer routing that avoids the small-tensor dispatch tax. The data dictates a highly optimized hybrid execution model. Early, low-dimensional layers and highly dynamic sequences are processed natively on the CPU. Meanwhile, massive, dense intermediate convolutions are surgically offloaded across the C-ABI boundary to the specialized silicon. But the primary scientific payload of the version 0.81 validation suite remains, determining if routing math to opaque proprietary silicon breaks the strict determinism required for auditable machine learning. This data table from the benchmark manifest analyzes the hardware's internal execution. Looking at the Intel Infer Repeat Forward metrics, the hardware produces exact bit-perfect outputs across 90 out of 90 consecutive runs. Critical limitations do persist. Because vendor compilers author the execution graph internally, they silently introduce floating point drift. OpenVINO currently fails to implement layer normalization consistently with first principles mathematics. Despite this compiler drift on specific layer architectures, the physical execution of the NPU remains perfectly reproducible. This standardized C-ABI architecture is designed to map this same layer-by-layer offload capability to Qualcomm Hexagon NPUs and Google TPUs. Deploying machine learning at the edge depends on building auditable, real-time orchestrators that bridge the gap between theoretical topologies and the raw mathematical power of fragmented consumer silicon.